Hi, MC Bling Daddy here, showing in Pseudocode how to set up Minecraft to produce roofing for all shapes of houses with diagonal and axial walls. You may want to review command block coding engine videos before you continue with this one, or if you have questions about things we've done before with the engine. In the CBC coding engine videos, CE vids, we introduced the coding engine that helps the user to create sequential command blocks to carry out equivalent pseudocode that mimics modern high-level programming language code. This time, we'll describe the logic that goes into the pseudocode shown in this video's comment section. Looking at the process of creating a floor or a roof for a building, you'll see that the floor is set down in loops made out of straight rows of blocks. And at the final block of each row, there is a change of direction to start a new row that extends out in a straight line from the final block of the previous row. So note that the final block in each row is not considered to be part of the extension process of the new row. Note also that there are some differences in the algorithm used in the video you're seeing versus the discussion that follows, but the general principles just mentioned are essentially the same. If we take a look at a diagram of how the tiles were laid down in the video we were just watching, we see the tiles laid down in the same manner. Starting at the origin, labeled with an O, the first row, labeled R0, extends off to the right a specified number of blocks, in this case 4. The origin is not part of the extension of row 0, an axial row so-called because it extends along the x-axis, but it is filled in at the end of the loop in row 7, which completes the loop. All the rows are specified to extend 4 blocks, and row 7 extends with 4 blocks diagonally. Extending a row inserts a block next to the starting point for the extension, but the starting point is at the end of the previous row, or also the origin, or also at the end of the loop. Since the row goes off in a straight line, the starting point appears to be part of the row, so in this case the row would appear to be 5 blocks long. But that means we would be double counting blocks at the corners. So there are a total of 4 times 8, or 32 blocks, not 5 times 8, or 40 blocks, in the outer loop. The number we specify is the extension count, not the visible count on the side of a wall. The main reason for doing that is because the for loop parameters for rows match the specification. To begin the second loop, it is necessary to start on row 0, but inside the first loop. And we need to start from a location that will allow all the blocks for that row to be filled in without overriding the first loop. The red arrow shows the loop 2 start point with respect to the origin. And, again, that block is not considered part of the row 0 extension. But we will see that it is filled in by row 7, as before. So we extend row 0 and all following rows in their specified direction as far as possible without overriding previous blocks through row 7. Note that if we extend row 0 as far as possible, it has the same number of blocks, 4, as it did in the first loop. The next row, row 1, is 1 block shorter. So is row 7 at the end. In order to effectively fill in the floor, or equivalently the roof, we need to know how long each row will be from loop to loop. Each row is the same length or shorter, but by how much? And the same kind of consideration applies when we move from loop to new loop, as shown by the red arrows. The change in number of blocks in a row from loop to loop will depend on which row is being considered, as well as what kind of row is before it and what kind of row is after it. Row 0 initially has diagonal rows on either side that bend away, and you'll see that when that occurs, it has the same number of blocks each following loop. But the diagonal row, row 1, loses half a block in length when it stops before the axial row, row 2. That's easier to see if it's enlarged a bit. There is no way to specify the extension value for diagonal rows in Minecraft because Minecraft arithmetic is integer. However, the same thing happens for the other end of a diagonal row. Its decrease is also half an integer, possibly 3/2 as well as 1/2. So added together, we always end up with an integer. That means we have to track how many halves we've lost, then divide by 2 at the end. If we gather these results together, we end up with a table detailing how many halves are lost depending on what type of row we're measuring, plus what rows lead up to it and which rows follow. Note that one unneeded measurement has been added in to demonstrate that the specific row number we're analyzing is not important, R1 or R7, but only what type it is, diagonal or axial. Other types of association can happen with different shapes of building. A triangular shape leads to very different changes in row length. The top one shown has 10 for the axial base at row 0, and half of that for each diagonal. It leads to a table that extends our first one with a new set of results. Another triangle with axial base and left side also provides us with some new information, but also duplicates some of what we had from before, shown highlighted in light red. Let's take a look at the pseudocode that's needed to implement these results. The pseudocode can be found in the comments section of this presentation. Discussion of the pseudocode here is somewhat longish, so if you're not interested in the details of the code at this time, you might want to skip to about 18:15 in the video. First, the declarations contain elements that are needed for most CBC programs. One of these features is that arrays are simulated with switches. Scoreboard objectives are used as index values. Although appearing as numbers, objectives are treated as text, so switches are needed to convert from one to the other. We'll see shortly that entity names like W and E are used to represent array names. For loops require an index and other values. These can be formalized as specific objectives. Cur represents the current index value as you loop through the for, named for an entity, for example L or R. And many other variables are needed for the specific purpose of iterating through loops of blocks, rows in the loops, and placing blocks themselves. Many of the techniques required here for converting pseudocode to Minecraft commands can be found in previous videos on command block coding, CBC, and in those detailing the coding engine, CE, that can do that conversion. In addition, many of the variables used here are detailed in the CE presentations describing construction of multi-unit housing, visible also in some of the frames of this presentation. If we look at the overall structure, we see the program is entered at the main setpoint label. There are nested fors that cycle through the parts of the construction, units, U, stories, S, construction phase, C, loops, L, rows, R, and block count, B. Since we're concerned only with the roof construction here, we'll be looking in detail at the R loop only. If you're interested in how the other loops work, take a look at the last of the command block coding engine videos that I mentioned earlier. Now looking at loop R, we see that it cycles through the possible rows, there being a max of 8, 0 through 7, starting with the first row that has an extension length greater than 0, and ending with the last with the same condition. There may be some in the middle that are ignored for the same reason. The initial range is set by the user as Rn and Rx, min, and max rows to be included. Each row is processed to calculate extension differentials. Extensions, E sub n, are how many blocks are added from the starting point of a row, so are actually one less than the visual length. This is done for a couple of reasons. First, to simplify coding, since the loop for adding blocks doesn't have to back off one to get started. It just goes forth from the block that the marker is already in. Second, it means one doesn't really have to worry about counting the blocks at the corners of the construction loops. The total number of blocks around the building is just the sum of the E sub n's. The computation of differentials, changes in extension count, is done in the sub get d2s in separate steps for the left and right end of each row. That's because for each row, the way we're for looping around, we only know what row precedes the current row, not the one following. But we'll see how that's done shortly. When we start a loop, we have to shift the position of the start up, and which way, or horizontally, and which direction. This will depend on what construction phase we're going through, what the direction of the first row is, and whether it is shortened or not. A series of subs can move the WC, the world cursor, in all the required directions, and that direction is determined using a switch. See previous CE videos for details. The next line of code is to mark the start location of the next while loop, and we're not really interested in that here since while loops are all the same length. There are some subs we need to get an overview of. Listings for these subs can be found in the comments section of this video. The get and set functions for arrays W and E are needed because Minecraft doesn't have array references in its scoreboard functions. Switches are used to get the nth element of the array based on objective var n. E and W values hold the value of the specific array elements being operated on, partly out of necessity and partly to speed computation in other parts of the code. The reset E method for loops through array index values 0 to 7 to set each element of E to the corresponding element of W. This for loop uses entity n with the for loop objectives, cur, rem, and so on, because Minecraft does have simple arithmetic functionalities to add a value to an index each iteration through the loop. Mod is the standard math modulo function taking two parameters n and m, returning m sub n. These are all objectives of the global var entity, short for variable, of course. Mod2 is used to compute whether a row is axial along the x or z axis equals 0 or diagonal equals 1. Mod 8 is used to compute the numerical distance between rows as needed for row shortening computations. If, for example, row 0 comes after row 7, the difference is minus 7. 0 minus 7. Mod 8 changes that to a positive number, plus 1. The numerical difference between the rows is 1. Diff is a function that calculates the shortening of a row as discussed with the diagrams previously. It uses rmod2 or m2 to determine if the current row is axial or diagonal, and r minus the previous row mod 8 to determine the numerical difference between the rows. Switches then determine the length difference for the row, actually doubling it or modifying it otherwise for computational purposes, as discussed earlier with the diagrams. The result is returned as D. Finally, we look at sub getD2s, which computes row shortening for the previous row as well as part of the current row. But first, we see the return code is placed before the entry point at the start of execution to make it possible to get all the code formalism out of the way at once, rather than having to wait until the sub is fully coded to place the return code. The sub is broken into two parts by a switch, the first handling walls when C equals 3, the second handling floors and roofs when C is not 3. C not equal to 3 is broken into two parts as well, one for the previous row, RP, for which we've already computed the left end reduction of the row and stored the result in D3, and can now calculate the right end reduction, and hence the total reduction, and which we can now store in E sub RP for the next loop. And one part for the current row, R, for which we can only calculate a reduction of the left end, storing it in D3, since we don't know what row will be next and how that will affect R. One complication in this process is that when we start the very first row of a floor or roof stored in Rn, which is placed in R1, we don't have anything computed for the previous row, starting as Rx, placed in Rp. So we simply skip that one and do it at the beginning of the next loop. For all successive loops, though, when we do the first row, we have to find the row that was extended last in the previous loop, Rp, so we can compute its row shortening for that loop. That's the tricky part about breaking the floor and roof construction into separate loops, so that we have to keep track of the order of rows over the for loop, stops, and starts. Tracking becomes even trickier when the last valid row of the for loop, Rp, drops out. That is, extension goes to 0. Then one has to figure out what the last valid row before it was, Rpp, so one has to track Rpp as well. Returning to the main line of code, we pick up after the getD2's call, but the switch that's used simply shifts a loop with respect to the one before it. It does require knowing how the position of the first row changes, though, so this code can't just be placed in the L for loop. It has to be inside R after getD2's. Finally, we've recalculated row extension changes where possible for the next loop, and we can now go ahead and set the blocks for the current row in the B for loop. Let's take a look at the code in operation. Note that we're only doing a single story to begin with, since that's interpreted as floor and roof only. First, we'll take a look at creation of a typical octagonal building to verify this code can recreate that. Next, we'll look at some alternative shapes, this one a slanted rectangle. Here's a triangle pointing left. Here's one pointing right. This one points down. This one points up. And here's a very irregular shape. To demonstrate that we haven't lost the multi-unit and multi-story functionality, here's a building with 2 units and multiple stories. Now there is a problem with this code, and that's why this video is only part 1 of what may or may not be a 2-parter. When there are 2 or fewer sides to complete on the very last loop of the floor and roof, it goes crazy. What you see is all but the last potential loop of the floor and roof being filled in. There hasn't been enough time to completely debug the code to fix this error, and unfortunately other priorities have arisen. So maybe someday it'll get fixed, but in any case, thanks for your patience, and thanks for watching.